Hello, everyone. Another episode and lecture for IITT, the International Interactive Technical Talk. It's a series. I think we are at number 12. I hope you are interested in watching the first 11 episodes. If not, you should watch this one because I saw a little bit what's coming up with the presentation of our distinguished uh, and colleagues that are presenting with us today. And I like to introduce them. Let me share my screen. So today it's TC104, and it's about physical modeling and geotechnical engineering. Is my screen full or not yet? Not yet.
Not yet.
Why does this disappear? Oh, here it is. Yes, I succeeded. So with us, we have Professor Anastasopoulos. He's presently in Zurich, Professor of Geotechnical Engineering at ETH, and he is the chair of TC104. And we are trying, as you know, trying to cover all 40 TC, which are subspecialties of geotechnical engineering. Thank you, Ioannis, for chairing this TC. Also with us, Professor Cristina Tsuha. She's presently in Sao Paulo, associate professor at the university there, and also associate editor of the Canadian Geotechnical Journal and member of the editorial board of International Journal of Physical Modeling. So specialize in this. With us, our Dr. Federico Pisano. He is associate professor of offshore soil mechanics at TU Delft, presently manager offshore wind USA in Boston with NGI. He's a vice chair of a tangential or sister TC, which is TC209 in offshore geotechnics. And hopefully he will give us a very interesting example. I can't wait to hear what you have to present to us, guys. And remember, it's interactive, so we can interrupt each other a little bit to animate it. And I am sure many people are going to be watching us later. I will stop sharing, and the floor is yours, Ioannis. If you like to share your screen, because you
Yes.
are starting.
Thank you. Okay, can you see my slides?
We can see your slides. I will mute myself, so we will have a...
Yes. So, hello everybody. I'm very happy to be part of this interactive talk. I will briefly present a few things about physical modeling in geotechnics, with emphasis on centrifuge modeling and how it can be used for innovations in practice, with a few examples. Okay, so why centrifuge modeling? Centrifuge modeling, we can model many different things. I would like to focus a bit on the example of earthquakes, because I think this is a good example to understand why this is needed. And you see here the biggest shaking table that exists in the world, in defense in Japan. In this shaking table, it is possible to test structures of up to 1,200 tons. You see it's about 15 by 20 meters. Buildings like this one, you see on the right, true scale buildings. So this is possible. However, when you start putting soil, the biggest, let's say, box we can use is about 6 meters tall. So even with this huge shaking table, we are limited to what we can test when we have soil structure systems. Also, it's extremely costly. One test in e-defense may cost something like 1 million. So centrifuge is the way to go, a possibility we have in geotechnical engineering. And a few words about what it is, what it does. So let's say here we have a field problem, 20 meters of soil, a pile of 15 meters. If we take a soil element down here, then the stress level is 120 kilopascal. If we scale it down, we have to scale it down. Let's say we use a scale of 1/50. Then the same soil element, you understand, the pile will now become 30 centimeters. The whole soil will be 40 centimeters. So the stress level here at the same level will now be 2.4 kilopascal. And we have scale effects because the response of soil is a function of stress level. It is a different material, friction angle changes, dilation changes, stiffness changes, everything changes. So what is the trick? We put our model in a centrifuge, we spin it, we introduce a pseudo-gravity field, so we multiply gravity by 50. So at the same location, let's say in our model, and now we get, you understand, geometry is reduced 50 times, stress level is increased 50 times, so we get the same stress level as in the prototype. So this is the trick that the centrifuge does. There are two types of centrifuges. You see our centrifuge here in Zurich spinning. The beam centrifuge, it has a swing. And as you can see in the video, while it is spinning and the centrifugal acceleration is increasing, this swing is also rotating. So this is an obvious advantage of a beam centrifuge because it rotates, so the model is always perpendicular, let's say, to the base. There is a second type, the so-called drum centrifuge. And here the advantage is that we can have soil going all the way around. I will not speak so much about drum centrifuges. I will focus on the beam centrifuges. A few examples, what you can find around the world. At the moment, there are at least something like 100 facilities that exist, maybe more. Perhaps the most historic one is the one in the University of Cambridge, the Schofield Center. And you see here how we measure the capacity of centrifuge. Radius, this one has about 4 meters, and capacity in G tons, so 150 G tons. So it can carry 1 ton of model at 150 G. Other examples include a very big one in UC Davis. You see now the radius is 9 meters, the radius, and capacity is bigger. Other examples from Asia, K Water, 800 G tons in these cases. And this is our centrifuge in Zurich. It's not brand new. It was used in Bochum for many years. We got it used, let's say, and it was refurbished. Of course, to do testing, we need to prepare our models, and to prepare models.
I remember the one in Boulder, Colorado.
Colorado Boulder, also a very nice facility.
I worked in, and when I was a student, I was in the basement, and they were putting together the centrifuge at Texas A&M University. And there was no protection between the centrifuge and my office. But they built a new one, a new protection later. I learned after they started, but I was always worried that I would see a box flying through the wall.
I hope there was some chamber or something at least.
Yes, they later built reinforced concrete, of course.
Okay.
But
yes.
at the testing, they told us, everybody leave your offices.
Yeah. Safety is an important consideration for centrifuges, for sure. So as you can imagine, we need to have strong boxes like this one.
Before, I want to interrupt you one more time.
Yeah, ask me
I know
if you like.
The beam centrifuge, but the drum, what is the advantage of the drum for what kind of test? You said because you can have the soil all around.
The advantage of a drum is that you can have soil going all the way around. So, for example, for our drum centrifuge, it has a diameter of 2 meters. This makes a perimeter of 5 meters. So, if you consider your equivalent,
that's the drainage or permeability and things like this, or
you can have a very long model, which is circular, of course. So, for example, if you want to test a lot of, I don't know, piles, you can have various locations where you are testing different kinds of piles.
Okay, the same test.
Yes. So in one test, if you have soil going all the way around, you can have various locations of testing, let's say. The disadvantage is that there is no swing. So if you are using boxes like these ones, actually these are from the drum centrifuge, this round one, for example, then this box you have to rotate by 90 degrees to install it. And as you can imagine, if your model is made out of sand, it will fall. So there are
Yeah.
tricks you can do there, taking advantage of suction so that the model is stable until you start spinning. There are
Yeah.
various types of boxes. There are boxes with windows, and these are useful, like this one, because you can do image analysis, you can take photos, and then you can do particle image velocimetry so that you can get contours of displacements and deformations. You need also things like this, sun draining systems. This is the one we have in Zurich, as automated as possible. So here, these systems are necessary to have models of controllable and repeatable density, relative density. It's important to be able to control what we are constructing and also to have repeatability. There are also things like this, robots, and here I'm showing robots from RPI in the US. So these robots can be used to do different operations in flight. So you see this one has 2 degrees of freedom. It can move longitudinally and also vertically. This one has more complicated 4 degrees of freedoms. They can have tools like this. So the robot can go to the edge, pick a tool, and then do something in flight without having to stop. What you can do in flight, for example, you can do CPT testing. So this is an example of doing CPT testing in flight. And this is important because, for example, when you do a test with liquefaction, you do a CPT before, you do a CPT after, so you can kind of quantify the differences in your model. For seismic loading, you need a shaking table, and this is, let's say, one of the first that were developed, if not the first, in Cambridge, the so-called stalled angular momentum SAM actuator. This could model kind of sinusoidal motions, but now these days there are more, let's say, advanced shakers, servo-hydraulic shakers. I'm showing here the one we have in Zurich made by Actidin, and here this can model any kind of real record, synthetic or real records. Of course, when you are doing seismic research, you need a box that is deformable, because in reality there is no rigid wall inside the soil. So when you are shaking, the soil would like to deform. So to allow this deformation to happen, as you see here, you need something like this, a laminar container. This is composed of laminates that are connected to each other through sliders. So when it's shaken, it is possible to deform. Another variation, and this comes from a University of Dundee, is the so-called equivalent shear beam. So here, instead of sliders, we have rubber. And the rubber material is providing, there is a shear, let's say, stiffness, and we call it equivalent shear beam because it is kind of mimicking the stiffness of soil columns.
I like this. Yeah. For
This is
small
really
strain,
nice.
yeah.
It's really nice, much easier to construct. However, with stiffness, this is the question. The stiffness of dense sand, of loose sand, of also for a specific type of sand, at small strain, at larger strain, the stiffness is changing. Of course, it is much easier, much less expensive because it's only rubber, it's not always sliders, and also it's much better in terms of maintenance. So many laboratories have boxes like this.
Are they interchangeable? You can modify the stiffness, have one test with one stiffness, another test with another stiffness, see the effect, sensitivity analysis.
It would be possible, but it's not so easy because, I mean, to change the rubber, it's a big effort. What you
It's a
could
big
do,
effort.
yes, what you could do is to install perhaps some plates outside and use these plates kind of to control the stiffness.
Rigid, yeah. You can limit the deformations.
Yes. In general, I mean, usually these are tuned to some average, let's say, soil column, and they are used like this. Of course, if you have large deformation problems, such as liquefaction, then the laminar box is a better option. But of course, the disadvantage is related to maintenance and cost of construction and all these sliders. It's more complicated. Another option that is used a lot in cables and not only is to have a rigid box with absorbing boundaries. Why a rigid box? A rigid box obviously not good, but it allows you, if it has a window, as this one has here, it allows you to do image analysis. Okay, so it allows you to observe the deformations. They use this duxil material, and this duxil material is very soft, so it can absorb relative deformations. So it is decoupling, let's say, the motion of a rigid box to the motion of a soil. And actually it works pretty well, provided that you are far away from the boundaries. What is happening in the middle is very close to what would be the case if you had the laminar box. So this is also a very good solution. But again, we need to have adequate distance to the boundaries. Now, I would like to mention a few research challenges. Again, I cannot mention everything. So a few research challenges that not only we are doing, but I try to make it more general. Challenges that we're trying to solve and for which physical modeling can play a crucial role. First of all, aging infrastructure. This is a structural example. It's the Morandi Bridge that collapsed a few years ago in Genova, in Italy. Here, the problem was corrosion, but this makes it clear that doing nothing is not really an option. I'm not saying they were doing nothing, but we have to do something. Collapses like this can become more and more frequent. So we need to devise ways to, let's say, to find ways to improve our existing infrastructure. Second, there is an urgent need to reduce CO2 emissions. I don't have to convince you about climate change. It is here, it is happening. The building and construction industry makes over 30% of CO2 emissions. So we have a great potential to reduce. We need innovative solutions. And actually, these are things that we can do as geotechnical and structural engineers. Climate change is bringing more and more natural hazards, heat waves, not too much water, actually not water at all, or too much water, extreme rain, like Medic and Ioannis a few years ago. And here I have an example based on actually the work of Labros Sakellariadis. This was a project on the retrofit of existing bridges and existing bridge foundations. This project was funded by the Federal Road Office in Switzerland, and it is related to bridges. Bridges are bottlenecks. So when we have increased traffic demand, we need to widen our roads. So widening of existing bridges is a problem. A second reason to retrofit is because these bridges are old. They were constructed in the 60s, maybe earlier, so they are not designed for earthquakes. And I have here an example of a real bridge that was widened. You see the widening here is in the form of an added part of a deck. And this part of a pier was there to actually to support the widened deck.
The corbel.
Yes, exactly. So what happens in this case is that you increase the weight, you increase the mass of your system. You need to retrofit the piers. This is not easy, but it's local. You have to do something here, okay? But if you need to retrofit a pile group, then this becomes non-local at all. You need to excavate, as you see here. You need to have adequate space to bring your machinery, install piles, doweling, and enlarge pile cap, so it can become a very challenging operation. What makes it challenging is that when you construct a new bridge, the bridge is not there. If you need to come underneath an existing bridge and install new piles with a machinery like this, then this can be quite challenging. Also, perhaps this bridge is inside the river, so this makes it also difficult. So there are big incentives to try to optimize. And you see here an example of two experiments. This is pushover loading using an actuator here. And we have two cases. The top one, you see here, is safety factor free, vertical safety factor. So this would be the original bridge. There is a pile group here underneath with two piles. And here we have, you see the mass is much bigger. We have increased the mass by 2. It's like we did widening, and our bridge now is 2 times heavier. So safety factor 1.5. And now, people will be like, 1.5, are you crazy? Yes, I'm not crazy, but we wanted to push it to the limit to see what happens, okay? And you see here, you see two things. First of all, this experiment, you see 2 lines. We did it twice to check repeatability. This is very important when you are doing physical modeling. And the 2 lines are very close, so this is not bad. And you see here that the 2 cases have a big difference. There is an overstrength. But be careful. The one that has bigger capacity is the one that is more heavily loaded. So actually, you are increasing the vertical weight of a structure. In terms of moment capacity, you get a bigger capacity. I don't have time to explain it. It sounds like a paradox, but if I explain you how it works, it's very, very easy to understand. So we need to devise better methods to understand how these systems are performing, develop design tools, failure envelopes. So these are things that centrifuge modeling can help us to do. So seismic assessment and retrofit of existing dams. This is another big thing. In Switzerland, but not only in Switzerland, I think globally this can become something very important. Switzerland has a lot of hydropower dams, and you see some examples here, some impressive structures. These were also built many years ago, and in some cases they are not designed for earthquake loading, or they are designed for something less than what we would do today. And we can have problems like this. This is the failure of a San Fernando dam during the 1971 earthquake due to liquefaction phenomena. So this is something we also need to tackle. Okay. Transition to renewable energy. I think Federico will talk about this subject specifically. So this transition is calling for migration to deeper waters. So we need new solutions. For example, I have two examples here. We have been working on, not only us, a lot of colleagues, let's say, doing research, guide support structures, and these support structures need to be anchored properly on the seabed, or suction bucket jackets. Also, they need to be understood how these perform. And these systems can be tested in a centrifuge to quantify their response. Climate change is bringing, as I showed previously, more and more extreme weather, and the problem of scouring of structures subjected to perhaps things that we have not thought so well before is happening more and more. I saw some examples here recent from Germany. So here, this happened because of an extreme weather event, a lot of flooding, also here. Or a case of a collapse of a bridge in Kalabaka in Greece a few years ago. So here, there is a flooding, scouring of a bridge pier, and we can have collapses like this. And I'm afraid that because of climate change, things like this will be happening more and more. It is possible to solve them. For this reason, we have developed this apparatus here at ETH. We call it miniaturized tidal generator. There are other variations, of course. This can model flood events and tsunamis. Both things are the same. You see here it has these tanks, and by controlling the water inside the tank, we can flush here our model. The model space is here. We can recirculate through this pipe, and we can have a wavelength that is even close to infinite, let's say. So with this, we can model things like this. A bridge pier subjected to scouring. You see that there is a scour hole that is developing here. And this brings me to the end of my presentation, where I would like to briefly show a few things about our GeoLab project. Okay, the GeoLab project is a project that includes a lot of institutions around Europe, and you see some examples here: University of Cambridge, Deltares, many more, Université Eiffel in France, TU Delft, and more here, big physical modeling facilities. And one of the scopes of this project is to provide so-called transnational access. So users can apply to have access to these facilities to do experiments in collaboration with the facilities. And in most cases, there is a lot of emphasis on problems coming from practice. So coming from the industry to solve real problems. I will show you, due to lack of time, only two examples. The one is a project they did in Cambridge. You see monotonic and cyclic centrifuge tests on piles in sand to provide innovative solutions. And here they did something very interesting. They designed miniature concrete piles with miniature rebars. So these are piles that can actually break. As you see here on the right, these are piles that can develop a plastic hinge. And what you saw in this video is the actual pile group you see here being pushed with this system so that we can see how the system performs as realistically as possible. A second example from Deltares, centrifuge modeling of pit
the one you showed is the cyclic one, right?
This was cyclic, yes. So you see there is a pulley, this anchor system here. There is an actuator which is actually pushing and pulling this, so you can apply also cyclic loading. Okay, monotonic loading is possible. There are systems with multiple actuators. We have a system that has two actuators. If you move them in the same time, you apply horizontal loading, or like this, you apply differential rotation. So there are various possibilities to apply different kinds of load paths. What is particularly nice for these tests, besides the fact that let's say the research question is coming from industry, is that you can actually see a plastic hinge here forming on the pile, which is not that usual, let's say. The second case, here the idea is to try to improve design and constructions of roads on peatlands so that we can reduce the operational maintenance costs and the carbon footprint from the excavation and replacement of the pit. Because usually what they do is they say, we have pit, you see the pit here in the model, we just excavate and replace it. But this can be very costly, both in terms of resources and in terms of carbon footprint. So here the test was done. You see here that the traffic load was applied with this two strip loads, let's say. And here you can see how it fails. So based on experiments like this, it is possible to develop, let's say, improved solutions, innovations that can really help practice. I think this is my last slide. I would like to thank you for your attention, and if you have more questions, I will be very happy to answer.
Ioannis, thank you so much. This is really good information and good start for this lecture. And I was really happy to see all these different centrifuge at work. And especially in the last examples, connecting practice to theory, which is what I love to do, design, build stuff. So I like here, if you stop sharing, to give the floor to Cristina.
Oh, hi. I will share my presentation.
Cristina, we have a problem with your voice, so speak slowly.
Can you see my presentation? Oh,
yes.
Sorry. Could you hear me, no?
Yes.
Yes.
But it's not full screen yet.
Okay. The sound of my computer is not very good, sorry. Okay, share the presentation now. It's okay, the presentation. I will start the presentation. And before I start the presentation, I would like to thank the organization of this interactive technical talk for the invitation. For me, it's a big pleasure to be here, participating in this talk. And I will show to you some examples of the use of model tests to complement some field studies that we have conducted at the University of São Paulo to investigate some practical problems, practical foundation problems. I separated 3 examples of foundation problems that we have investigated in research projects at this university, at our university. The first example is solutions to use shallow foundations in collapsible soil. That is very common in Brazil. Normally, it's unsaturated soil and lateritic soil that are collapsible, high porosity soils. And it's very typical in Brazil, some wet-induced collapse settlements during raining periods. This is a very, very common problem in Brazil. The second problem that we have investigated is the performance of helical foundations. This type of foundation becomes really popular in Brazil for supporting of towers of transmission line power. In Brazil, we are a very big country, and we have an immense energy transition system. To have some idea, for during 10 years, from 2020 to 2030, we have a prediction of around 37,000 of kilometers of transmission lines. And in many of these transmission lines, we use helical foundations. Normally, when you need some deep foundations, it's very common. This type of foundation started to be used in Brazil, I think, around 15 years ago. And you have no studies, no good models for prediction. So we are studying, I think we started in 2004, investigating this kind of foundation for guided mast tower, to support tension load and compression load in self-supporting towers. This kind of investigation, we have conducted many projects with the industry of helical foundations and projects for the National Agency of Energy Transmission in Brazil So we have the financement of industry or government for this kind of work. And more recently, we start to investigate the possibility of using energy piles is to extract shallow geothermal energy, something new for us, in Brazilian soil condition and climate. This is more typical in Europe and USA, but in Brazil, something new. We did some field investigation to investigate for this first case of energy piles in Brazil. That is a building, a case study constructed at the University of São Paulo. Now it's under construction, not finished yet, but the foundation, we installed energy piles in 2019. We installed pipe, steel piles, and CFA piles. And for the pipe piles, we have investigating the best filling material to provide better thermal performance and lower costs. We also investigate the effect of groundwater flow in the thermal performance and the effect of the operation mode. Because for us in Brazil, we need geothermal energy for cooling much more than for heating buildings. So we have a kind of unbalanced system. And in this case, the operation mode is very important to keep the system efficient. The first study, the use of shallow foundation by reinforcing the soil with lateritic soil columns, is a kind of new solution that we proposed to allow the use of shallow foundations in collapsible soils. These soils normally are lateritic soils that present very, very good soil properties when compacted. We have some experience in this material compacted in roads, embankments, dams. And this soil, when compacted in laboratory and the field, you observe that you have no problems of collapse. So normally for foundation in this kind of soil, typically you use piles or footing and a very thick layer of compacted soil, controlled soil. This typical solution, the compaction takes time and money, also piles too. So normally is for small structures or medium structures. We have very huge foundations, and in some cases is expensive, and some poor cases for poor people have no money to construct their houses in this kind of soil. So we developed some economic solutions, low cost solutions. The solution was to propose compacted columns of the lateritic soil. The idea is to use the local soil as a filling for the columns without adding other materials. It's a kind of economical and environmental friendly solution. Have no concrete, no cement. But before we have the idea, and this solution was never constructed before or tested before. So we went to the field to verify the feasibility of the solution. So we propose a kind. Wait, sorry.
I will steal this innovative solution for Nigeria. Lots of lateritic soil there.
Oh,
Nigeria
good.
and Brazil,
I want to know about that. Oh, good. I'm very interested in this topic. Oh,
I saved the screen. I will. You gave me ideas.
Oh, good.
We use stone columns. Now
It works really well. Yes. And it is not expensive. I show here. You can see.
It's
we
amazing,
use a kind of simple and cheap free-fall hammer. And as the soil is high porosity, it's really easy to open the hole. You're only using a free-fall hammer. And after opening the hole, we compacted the soil. We control using a kind of volume control. It's a simple technique. And it can be able for any.
Simple is better.
Yes, simple is better. I agree with you, Marc. Simple is better and cheaper,
especially in a country like Nigeria.
Yes. Nice. It's nice because they also have kind of lateritic soil and in some places.
All the roads and road embankments we use lateritic.
Oh, good. We have published this. I presented here the publication, and if you need, I can pass the details. But we have know how to find a good and cheap procedure, so we developed this in a thesis of Freitas. It was a master student. And to test the solution, we performed many field plate loading tests. We executed many similar columns and did some plate load tests. We performed some inundation, and we observe again in capacity and reduction in the collapse settlements. Also, another idea was to verify around the column if the soil was improved. So we also did some sampling of the soil around the column here. We observe a kind of decrease of the void region around the column, so a kind of improvement around the column. And this is published in the Ground Improvement Journal. It's not very new work. After finishing the field work, we want to perform group tests, because the idea was to use this kind of columns in group. And to perform, to verify the effect of spacing or different configuration of groups is expensive, takes time, and we need a higher equipment for reaction for the loading test. So many limitations to verify the group behavior. In this case, we think physical model is a good idea to investigate the group behavior. We have a colleague in the University of North Fluminense in Rio de Janeiro. We have two centrifuges in Brazil, in Rio de Janeiro. The idea was to investigate, reproduce the installation, open the roll after compacting, reproduce the installation procedure and the different configurations of group. And we did a footing loading test for different configuration of groups in centrifuge, 10G. Also, we did some exhumation to understand the shape of the columns and compare with the field observation, and it was similar. And the results was really good in centrifuge. So we tested with different configurations of group, and with columns, we inundated the soil, and the performance was much better compared to the soil without reinforcement. And this is also published almost 5 years ago in the SC Journal of Geotechnical Engineering. We also did some numerical models, but this is a kind of, the model test was very, very useful for us to complement this investigation because of the group. The second problem that we investigate is the behavior of helical foundation.
You said this was published in the ICE proceedings?
Yes, 2019.
ICE, you mean
Journal of
Institute of Civil
Geotechnical
Engineers?
and Environmental. Yes.
Okay.
Journal Geotechnical and Environmental Engineering is a very good journal of geotechnical.
Yeah, see, yeah.
Yes,
but before you said proceedings of ICE, you meant
the field test we published in the Ground Improvement Journal is of the ICE.
That's in England, right?
England, yes. In England, the field test, and for the American, the model test. American journal. Okay. Good.
That's good internationally connected.
Yes. This is published. It's old.
Very nice.
Good. Thank you. And the second,
I will definitely call you when we have the next project in Nigeria.
Oh, thank you. Good. I'm interested.
You're the expert.
For us, it's very important because we have some poor people groups that have no money to construct the foundation, to pay for pile foundation. So we have a house with some problems of settlement, very bad. It's a kind of social work that we also should do at the university. So this topic is important for us. Changing the topic. The helical foundation is very important too, because we have many transmission line towers, and our big projects in the university is related to transmission line tower foundation. So we did some field tests. I did my thesis on helical foundations. It started in 2004. I investigated this kind of pile, and after we complemented with centrifuge tests and the calibration chamber test. So we use 2 different techniques of physical modeling to complement our investigations on helical foundations. This kind of foundation is very simple, is composed of a steel shaft, and some helical plates are welded to the shaft, and the pile is screwed into the soil, and normally used when you have kind of important tensile loads. We perform a test on instrumented piles. We did tension, monotonic, cyclic, in field. We tested the pile group, lateral load, compression tests, many tests. In the field, we also did some soil sampling around the pile to verify the installation effect around the pile. We did some CPT after installation, pile exhumation. Here, it's me here. After a pile exhumation to understand the installation effect, what happened to the soil. So we did many field, and it was very good for us, but some aspects to verify some models, analytical models for prediction of capacity and other problems as installation effects, and we need more complex tests and more repeatability. So we associate with a group, very good centrifuge, University Gustave Eiffel in France, Professor Luc Torel. He did a kind of cooperation and to have a better understanding and to complement and clarify some field observations. It was very, very important for us, the use of centrifuge models. Normally we use dense sand or loose sand. To the installation effect, we could do some exhumation of the pile after loading test and installation. We also use in France the microtomography, something very difficult to field, to understand the effect of installation after the passage of the helical plate, what happened with the soil, the density is reduced, so to improve the models for calculation. The effect of installation is very important, and in centrifuge, this is the thesis of Schiavon in 2016. Also, we published in the Canadian journal, Geotechnical Journal, this kind of tests to verify the effect of installation in 2018. In Nantes, in the University Gustave Eiffel, they developed a kind of equipment to install helical piles in flight and measure the installation torque. They developed a very good, so we could perform many simulations, many installations. It was very advantageous to verify the effect of pile geometry, to calibrate some analytical models. In field, you have some limitation, and in field, you also have a variability of the soil. So if you can isolate the variable geometry, you have some of the same soil. If you know the properties of the soil was very good, so you test a different pile configuration. We test instruments for the pile, and also for cyclic load. It was very important, because in transmission line, the main load is the wind load, and you have kind of cycles during the lifetime of the tower with different amplitudes, and we have the phenomenon of the fatigue, don't know English, I think it's fatigue, degradation of capacity, and we perform it in field, but it's very expensive and takes a long time to perform a cyclic test in field. We cannot test many parameters, vary the amplitude in many tests. It's complicated. So in field, we perform 50 cycles. And in centrifuge, we could perform many cycles in many piles, more than 1,000. I think we also performed 2,000 cycles to observe the pile degradation, the capacity. We did some work, published some work in Geotechnic Letters, Canadian, in the International Journal of Physical Modeling of this test, the cyclic test. It was very important for us, this combination of the field and the centrifuge for some aspects, and the cyclic load is one of them that good complementation. And some problem. Sorry.
Cristina, when we're talking in practice, because I saw your illustration of the tower with only one helical pile under each column.
No. No, you
That's
have
just, I want to clarify for the viewers.
No. Mas illustration, I think at the beginning. Now we have you're
So it's a
working
group of helical
group.
piles under each column, just to clarify. And do you play
I think
more
it's
with the numbers, or also you play with the size?
Yes, we play with the size, number of helical plates. We also work in groups sometimes. Vary inclination.
What is
We
the
did
largest helical pile? Because you need a high torque machine.
we need a torque machine. To install the pile, you need equipment to apply a rotation. We measure the torque because the installation torque is proportional to the capacity. There are some correlation using the field
And the
to
soil
the
type.
capacity control. Yes.
Yeah.
We have in centrifuge.
But what diameter are we talking? Are we talking 6-inch to or 200 mm?
Depends. For helical piles for transmission line, I think the bigger one is 16 inches or around 35, 40 centimeters, né? Or have small 25 centimeters to 40 centimeters.
Yeah,
This
the
range.
common ones, do they have square shafts? Do you use square shafts?
Yes,
Like
in the
in the
beginning.
US?
Yes, in the beginning, the first helical piles in Brazil, I think in 1998, in 2000 year, a long time ago.
That's how
The
they
first
started.
helical piles was in the beginning was from AB Chance, né? It's an American company. We used some pile chance, but after now, I think many companies now fabricate helical piles in Brazil. Different companies. In the beginning was just now I think 6, 7. It's increased very, very quickly in Brazil for the transmission towers. So, but the most are round
I just
shaft.
wanted to clarify that it's not one pile under but a group under each column.
Yes, it depends
And
on the
this
load.
group is not vertical because you have lateral loads, the wind loads. So you install them inclined?
So it depends. For guided anchors, sometimes it depends on the load. Small towers, you can use one single pile with more ELAs. For self-supporting towers, normally it's group of it around groups of 3, 4 piles, and depends on the load. It's variable. But we use a group.
Have you heard?
The example, I show only one part of the tower, not all the tower, né? Because you have 4 cables normally, 4 cables, né? In the towers. When you use,
Have you
you
heard
can use
of
only 4 stations.
the word reticulated formation? Ioannis, Federico, have you heard this word before? Reticulated formation? This is when you put a group of micropiles in all directions. So some are like this, some vertical, some. So you put them in all directions, like the roots of a tree, because micropiles came from Paliradici, the roots of the tree. And apparently they carry more vertical loads than if all of them are vertical. And if just vertical load, and the advantage is also they take better lateral loads. Reticulated formation. Look it up, Cristina. It's a little bit my specialty.
I have seen something like this in the geotechnical engineering. A group that using some simulating roots or some biological some things of the nature to pile foundation. I think interesting. This is interesting. The anchor
because you can
is very
install it in any direction. That's
the
optimized.
Yes. Because you have moments, horizontal load, lateral load. But
Yeah,
for
so
groups of
imagine
piles,
you have 2 piles like this and you're pushing vertical.
But in Brazil, when you use a group
resultant.
of tiles, we use vertical combined with some inclinated because we have sometimes horizontal load and vertical load. Sometimes we combine it, inclinated and vertical for self-supporting towers. But only
Sorry
one
to
direction, not
interrupt.
different
Keep going.
direction.
I got excited.
Yes, I like this this topic is very interesting, the anchors and when you have combined load, horizontal, vertical, tension, compression, is very
We're
nice.
running out of time. You have to go quick.
Yes, I should go quickly, sorry. So this is published. And finally, we also did some model tests using calibration chamber at University of São Paulo. We construct a calibration chamber in 2016 to focus the investigation on the micro behavior around the helical plate. We always want to understand the anchor effect, kind of zoom. This is also published in Canadian Geotechnical Journal. So we test different conditions of confining stresses, and we instrumented piles. We also put instrumentation on the soils, and I will go quickly. This is published in Canadian Journal. We verified installation forces, some effects due to the helical shape. And we also calibrate a kind of prediction model to the capacity of the helical plate, to the tensile capacity. This we could do in model tests because you can reproduce the soil, control the condition of stress, of confining stress. So it was very good work with controlled conditions to improve the prediction models. So finally, the last example, I'll go quickly because of the time. We have investigated the energy piles, steel pipe energy piles with different materials inside, filling materials, for the first case study of energy piles in Brazil. Our question was about which one would be the best filling material to fill the pipe piles that's open inside. We start in this case by model tests. We did a kind of test, a section of a pile. We tested different filling materials, water, sand, grout, steel fibers. There's some different piles to verify the better performance to transmit the heat transferring the soil. And it was important to have the decision for the field test. So after that, we investigate the use of 4 different filling material in the field. This is a case study that will be a real used for geothermal energy for a building and its construction at the university. So it was really important, the model test, to have some idea. And after the field test, we published it here in the Renewable Energy. We observe the thermal performance by the thermal resistance, the difference in the 4 cases of options of filling material, and we also compare with the costs. And this is really important for us, the first initial model test to guide for the field tests. We also evaluate the effect of ground water flow velocity in the field. In another kind of piles, CFA energy piles, in the same site. We did field tests. We also did some field tests, in situ tests, to measure the groundwater flow velocity, not sample, in the field, the variation along the depth. And we did some thermal performance tests on the pile to understand the effect of the groundwater flow velocity along the pile transmission, heat transmission. So we could observe the effects of the groundwater flow, also published in a journal here by PC. We did ISSMGE model test in a big box, simulate the flow with different velocity in PC. Is a thesis. And now, to finish this presentation, I have a student in France, in the University Gustave Eiffel. She's now performing group tests of energy piles to evaluate the effect of a group or the effect of operation mode, and also the effect of groundwater flow velocity, different configurations. And I think we finished this in January. So we show here another example that we keep using centrifuge models to complement our field studies. So finally, as conclusion of my presentation, we have work combining field test and model test at the university. For us, for the topics we have studied, it's a kind of complementary techniques. Some things we cannot obtain by field, but we can in model test. also numerical modeling. And for us, I think that is very, very advantageous, the use of physical modeling. More economy, I can test many piles in few time and the low costs. And I can control the conditions of the soil, the type of the soil, stresses, instrumentation. We can use different instrumentation. We can instrument the pile that we cannot instrument the soil, for example, in the field. The repeatability is important when we want to calibrate a kind of analytical model or a conceptual model. So it was really, really helpful for us. And I think you have a good experience combining these two techniques. Thank you for your time, and sorry about the time. Thank you.
Cristina, this was a beautiful present. We can feel the passion in your research. We'll be back.
I'm very passionate.
In January, when the results are out, you'll be back. But this time I'll give you 24 hours, not 15 minutes. Present.
Okay,
You did so much. Thank you so much. Very nice.
Thank you.
Federico, you started. Amazing.
Can you see my screen?
Yes, the floor is
Good.
yours.
Yes, thank you. Thank you all.
Great.
So I'm going to give a short presentation about the role of physical modeling in the design of offshore foundations. In particular, I'm going to take an example that is close to my activities, which is the case of monopile foundations. And as it was mentioned before, my work is kind of tangential to the field of physical modeling in the sense that I'm more of a numerical modeler myself, but I've been leading research that included physical modeling bits. And for that, I actually sought the assistance of my colleague at NGI, Wang, who checked the soundness of the contents that I was going to present today to make sure that a real experimentalist would approve what I had to say. So a little background to what I would like to discuss, and this is in a way like an appendix or a complement to what Ioannis was covering about the many areas in which physical modeling can make an impact. And certainly offshore foundations for offshore wind is one of those. And you can see here in this figure how in time we witnessed the evolution of the size and power output of wind turbines up to the latest models that are being deployed in current offshore wind energy projects. And this doesn't seem to be the end, because basically manufacturers are challenging each other in a rush to produce the biggest machine that is possible to find in the market. And you can see here on the right something that was announced just a few days ago by Mingyang, the main manufacturer in China. They're looking to release in a few years a turbine that can provide 22 megawatt. That's huge. And we're already approaching structures that are becoming as big as the Tour Eiffel. So, you see the challenge here. Now, the challenge for civil engineers, both the structural and geotechs, in fact, is to try and make sure that we are not overusing fabrication material, because that would be too expensive, still as expensive. So you would like to optimize your design, but not only from a point of view of fabrication, also from the point of view of mobilization, installation. We need to have things that we can actually move and install. Otherwise, we may not be able to develop our wind parks offshore. Here, this is a figure that is similar to what Ioannis showed earlier. Like, there are a number of concepts that we could use to connect offshore wind turbines to the seabed. We have a fixed bottom concepts. We have floating concepts that are used or are going to be used for deep water developments. But certainly, so far, the concept of a monopile foundation, which is basically a large cylindrical tube, has been the one that has encountered the most success so far, because of a relatively conceptual ease of design and installation, fabrication. It's been so far the most solid and understood concept. However, unlike flexible piles that have been used in the civil engineering industry so far and also offshore, like these monopiles are known to be very large in diameter and very short in terms of aspect ratio between embedded length and diameter. So you could see here an example, which is not even very recent, about how large a monopile could be with respect to a normal person. So then that's myself here in the port of Rotterdam in the Netherlands. Like the size is obvious, and nowadays people use much bigger foundation than this one. So when it comes to geotechnical design drivers, some of these are standard. Of course, you want to make sure that your pile has enough capacity. You want to make sure that the steel structure overall sustains fatigue over the operational life of the foundation. But there are some requirements that are pretty peculiar of this offshore wind development that we're following nowadays. For instance, the fact, and this is the latest point right here, that you need to design a monopile so as to you can guarantee as a designer that over the operational life of the foundation, you will not exceed a very tight limit in terms of a permanent tilt. And this is because manufacturer provide this tilt. And if you want your design to be certified, you need to make sure, okay, this is something that is not going to happen. Otherwise, you may not get your design in the right place. Now, sorry?
2 degrees?
It's less. It's like in the order of 0.5.
0.5?
Yes, over the operational life. 2 degrees is the number that people use to quantify the conventional capacity, lateral capacity. But you don't want to achieve that limit, because that would be serviceability-wise unacceptable.
2 degrees is a considered limit of the failure, ultimate.
Yes, yes.
And when you're talking monopile, are we talking monopile with anchors or just monopile?
I'm just talking about a plain monopile in this
Plain
presentation.
monopile.
Yes, yeah.
And this pile that is above you was filled with concrete, or it stays hollow?
It's driven into the soil and it stays hollow.
Driven.
So there is a soil plug, but there is no concrete filling. No.
No concrete filling. And do they treat it for corrosion, like epoxy coating and things like this, at least at the top? Or?
I believe they do. It's a little beyond the kind of things I usually look at, but yeah, there are corrosion issues that the industry and the manufacturers need to deal with. So of course there is something that is looked at. And what is important here from a geotechnical point of view is that each one of the design checks that one may need to go over are affected in a way or another by the behavior of soil under cyclic loading. So you really cannot escape in this area of business to deal with the cyclic behavior of soils and interacting foundations. Now here, I try to create this summary in which you can see on the left our engineering questions that span drivability, capacity and fatigue, and general serviceability requirements. And on the right, analysis approaches or research approaches that people resort to try and overcome these challenges. And you see a variety, like actually resort to each one of them, including large scale, centrifugal testing as a way to test a smaller scale, and numerical simulation. Actually, people are happiest when they can see, a complementary confirmation that one technique leads to results that are in agreement with what you will find, along another way of doing things. So just specifically to this application, why centrifuge testing? Of course, Ioannis has covered in much more detail why broadly we need centrifuge testing. I thought here for the case of monopile foundation, a lot of the pros that were mentioned still apply. So you may have the possibility to check qualitatively and quantitatively the performance. You are working with the soil, which is the real material that you put there in the centrifuge. You're not dealing with a model or a numerical modeling of it. And certainly you have a way of controlling testing conditions and ensure repeatability that is superior to what you can many times do in the field, because that's obvious, right? And the problem of cost has been already mentioned and also applies here. Like a field test for large monopiles are incredibly expensive and many times undoable, while you can do very rich parametric studies in the centrifuge that are going to give you way more insight than one single test that is going to cost you a fortune. So this is a very convenience that is possible to find, and it's a proven methodology. Like the offshore industry tends to believe that centrifuge testing works and gives credible insight. So there is also this traditional, level of confidence that the industry has been building upon and will continue. Now, some caveats or warnings, let's say, of course, like you're using a soil that is the same, but you cannot rescale soil as you please. Like you need to work with real soil. So in using and selecting a certain material, you may not be able always to perfectly scale how, if we're talking about granular materials, how grain size relates to the roughness of your pile or to the thickness if you consider, like interaction with the tip at the bottom or even during drawability. There is a challenge about how you reproduce in a centrifuge installation techniques that are becoming more and more complex nowadays and very dynamic. So scaling laws are challenged by the possibilities that a centrifuge facility offers. And then there are also, concerns regarding the scaling laws when applied to materials with very nonlinear behavior like soils. Like, is there going to be, at the end of the story, some net effect of the G level that you include in your analysis experimentally? Or you may just say, okay, as long as you do your scaling properly, everything is going to be perfectly consistent. These are questions that a number of researchers are giving contributions, very nice contribution. I just wanted to resume a few for everybody's convenience. So with respect to the problem of representability and repeatability, like there was just a few years ago an interesting consortium effort that involved a number of facilities using centrifuge all around the world, you see here. And basically, these facilities were all working on monopiles installed in very similar sense. You can see the PSD was very similar in all cases, so fine sand. And but they were using very different systems, like different actuation, different working principles, and different data acquisition systems. But what they could find is that if you are comparing situation in which geometrical and general testing setups are relatable, you're going to find very similar behavior. And particularly after normalization, you will find that the normalized behavior of the monopile under lateral loading is nicely consistent, and maybe one or two outliers were found, but people were able to explain why you would find that. Then the problem of installation, like this is very much at the frontier of R&D right now. Like a few people, like at the University of Western Australia or in France in Nantes, the FL University, they're trying to study how changing the installation method impacts the lateral behavior of your monopile foundation. There are results that are showing interesting effects and proving that the impact of installation may not be neglected in your lateral behavior kind of analysis. And about the level of the net effect of the G level, like this is a quote from a study that was performed at the University of Western Australia in cooperation with Oxford University, where people say that the lateral deflection accumulation of a monopile under cyclic loading seems to have, as you can see here, a net dependence of the G level. So it may not be incredibly apparent if you look here in terms of normalized lateral displacement versus number of cycles, but stresses the importance of try to reach in your centrifuge testing a level of scaling of your prototype that is consistent with the real objective that you're trying to model for reality purposes. Now, this is just a few words about an initiative that I've been leading in the past few years in relation to my work at the TU-Delft, which is the MIDAS project. Like we have the ambition, the project is almost over, of producing a new family of cyclic soil reaction models that can be used for engineering analysis. But this endeavor is backed up by a work package of centrifuge testing that interacts with numerical simulation of the 3D type. And here you can see, like in Delft, we were blessed with the possibility to access two different centrifuge facilities, the one at TU-Delft and the one at Deltares. They are in the same place, actually, just a few steps from each other. And they are different in size. As you can see here, the specifications. The one at the TU-Delft is much smaller and allows you to prepare samples quickly and run parametric studies. While we have the facility of Deltares is much larger, so it will allow you to model a larger prototype, so closer to reality. But of course, it takes a longer time. And we thought it would be a good idea to, test with these two facilities to try and understand the scale effects, but still also have the possibility to run many tests and have some tests that will replicate reality. And of course, credit to the masterminds that were behind all the testing program, with whom we work very pleasantly in the past few years. So credit to them here on the slide. You can see here, I'm just gonna go through a few highlights. You can see here how we use different monopiles of different size that we instrumented with strain gauges pretty heavily to try and then post-process the results to obtain a PY curve, so soil reaction curve, as accurately as possible. And here you can see the setup at Deltares, where we were able, due to size, to install 3 monopile at once in the same bucket, after guaranteeing numerically that you wouldn't have a significant interaction effect. There was obviously a concern, so we did a check on that before. Here you can see how the test worked. Like you can see, these are movies from 3 different moments of the same test. So same spinning event, while you will first work on one pile, then the other, and then the other. So there was, let's say, a smart idea to do things while using a single spinning of the centrifuge. You can see here how the acquisition system works. So there was an applied cyclic loading that would subject the pile to displacement and the strain gauges to deformation that we would able to acquire through the acquisition system real time. And from the point of view of the response, these are the kind of things we wanted to see. Like you apply different packets of cyclic loads, for instance, in this case of increasing amplitude, and you would see how the rotation of the mud line would evolve in time. Regardless of the numbers, the specific numbers, like this effort was useful because it gives us data that we can use for conception and validation of numerical models, which is the ultimate goal of the project. And on top of that, another couple of remarks, like prior to each test, we performed the mini CPTs in the centrifuge, and that would allow us to obtain compenetration resistance in our soil sample that would eventually, and already is, like inspire the conception of calibration procedures for PY models. They use CPTs as an input, and that is very important for design practice, because let's keep in mind that wind parks are systems with tens up to hundreds of structures. If you have a way of using direct sat investigation output to calibrate design models, as opposed to going to the lab and do way more lengthy testing campaign, that's at least in a stage of preliminary design, that's incredibly valuable to designers, because it's going to make things much faster and, you know, open to automatization, which is really, really important for the whole feasibility and time scale of this endeavor. One last point I'm going to touch upon is the problem of drainage, which is very well known in the physical modeling community. Like in working with a smaller model, you typically alter the way in which the water or the pore fluid drained through the soil and the timing of it. So you need to be very careful whether what you are testing in the centrifuge in terms of drainage conditions are representative of reality. People have come up with quite ingenious solution over the years, which is about, instead of water, using a fluid with enhanced viscosity but same density of the water that would allow you to keep the same stress level in your soil sample, but play with the drainage condition depending on the viscosity that you are able to retune. And obviously that cannot be done at freedom, like there are going to be constraints about it. But you can see here, for instance, in an event of monotonic loading that is very slow, in both cases you obtain a lateral response of the pile that is very comparable regardless of whether you use water or the viscous fluid. And this is because the event was slow enough for both situations to behave in drain condition. But if you engage in a cyclic testing exercise, then you're going to see that your choice about the viscous fluid is going to be quite influential with respect to the kind of pore pressure that you find. So this is not to mean like how things should be done, but it's only to inform about the problem that is there and how tricky it is sometimes to basically combine and make verified all the scaling laws at once while you have many requirements to satisfy. And this is my very last slide, like moving from structures that are subjected only to wind and waves towards seismic loading condition, which is very relevant to the Asian market, for instance. There is an importance for testing monopiles under seismic loading conditions. And this is something, including liquefaction effects. And this is something that we are about to do in our new project, Donicis, which is led by the TWelfth and in cooperation with ETH. So actually, The physical modeling campaign is going to be done using the same centrifuge that Ioannis showed earlier during this chat. And I would like to maybe make a comment, like somebody may ask, okay, like earthquake modeling has been done for pile foundation for a long time. What is more left to do about this? And I certainly acknowledge that a lot of research is there, and but what is important to retry and reassess is that we are changing design drivers and we are working with piles that are geometrically quite different from what people have used for other kind of civil infrastructure. So we may end up, and I would be happy to, confirming some of the knowledge findings that have been already, reported in the literature about seismic behavior of piles. But I believe there is room here to also find things that have not been pointed out yet. And this is basically going to be the task of this project that we are about to kick off. And there are many offshore wind developers involved, so we would like to make an impact also in transferring the results of our research toward the industry practice. And I believe this is pretty much all I wanted to share. I hope I didn't take too much time.
It's okay. It was so interesting and exciting to see all of the details of the research, because this is the new trend and the new coming size of projects and interest in renewable energy. And
yeah, certainly an important topic nowadays. Yeah.
Yes, especially going offshore. And before I conclude, I want to share my screen to show you something kind of a bit fun. It's in my years of practice, but basically when I was doing research, I solved analytically, mathematically, the pile behavior under cyclic loading. And I want to share with you, since, it complements the topic and it's a bit funny, the solution of y as a function of z and t in font 16 was 33 meters long. So just
That's
imagine
impressive.
when you're doing this fluctuation motion dynamically, every time the computer, the program has to go in the subroutine and run this equation. Definitely not, you cannot do it by hand. Here is another picture. I made my workers carry it by hand so they know how important their work is.
Thank you for confirming.
So,
yes.
Yeah, this is the effect. I don't know if it's working here. You can see fluctuating 2 centimeters at the top. That's one example. We're not going to elaborate. But this is the solution of the equation, showing how the force can be ahead of the movement. And if you go very fast, the force goes, same force going faster will not move the pile much.
Oh, yeah.
And it shows and the new solution solved the mystery, the missing link between rigid behavior and flexible behavior, depending the soil structure interaction. And I always give the example of you carry a fork in your hand, and the hand is your finite element or discrete elements, and you put the load. If the fork goes straight, that's rigid, and if it flexes, this geotechnical engineering is fantastic. And these lectures, thank you so much for being here, show really everybody how important our profession is. It shows especially structural engineers, because they are the most who make our work like, oh, it's simple. No, it's not simple. Geotechnical
We try to
engineering
stress
is way
that
more
every day.
Yeah, we face it all the time. Thank you so much for being with us. Ioannis, I want to congratulate you because you're the only one who respected the time limit. But I want to thank everybody, of course. And hope to see you soon, physically, one-on-one, personally, in coming conferences. And if you have if you want to add something now, go ahead before we stop recording.
I will just say one thing. I think the lectures of Cristina and Federico showed very nicely how important it is to combine different methods. And I liked very much that Cristina, in all the cases she showed, she had done field tests for large scale, centrifuge and numerical analysis. And this applies also to the things shown by Federico. And I think that, you know, avoiding completely scale effects is practically impossible. Whatever we do, scale effects will be there to some extent. So I think that the nice solution is that you do your centrifuge tests, you model the conditions of a centrifuge tests, you validate your model, and then you can use your numerical model to go back to reality. So this is a technique that I find very nice, and we try to apply it, you know, anytime it is possible.
All
Yes,
the methods
totally agree.
are for guidance. In the end, it's engineering judgment that should take control. Because you see the young generation that just jump on Plaxis. Please, guys, don't do that. Yes, Cristina and Federico marriage, that's what I call my lecture. Marriage between theory and practice is the best solution.
For me, I think my presentation is the most simple. I don't have many beautiful equipment like Ioannis showed, the centrifuge, the very modern robots, and also Federico. My experience is more with field tests. I'm a field engineer, geotechnical engineer, more than academical. I also do in design, so more simple things maybe, but it's important too. And the physical model, I think, is a very good tool to helping the practical engineers if calibrating models and other activities.
I encourage you to take a look at the other ITTs, especially the one on observational methods, because it complements a little bit what we discussed. Thank you so much. Anything you want to add, Federico, before I...
No, I think we covered all. I try my best to stay accurate through a topic that is, as I said, is not at the core of what I do, but I try. Thank you for having me.
Thank you so much.
Thank you all.
Bye all.
Thank you.
Bye-bye.
Thank you.
Bye. Bye.
Bye.